All right, we should be live for Worldcon office hours, I believe. I should be transmitting. I think I do see myself now. Exactly. All right. Things are going. My pod has started. Welcome, everyone. Welcome to week 4. Inching closer to almost the completion of this unit, right? All good things must come to an end. We're almost there. Let's see who's out there joining us so far today. Hope everyone is doing fine. It is fall in the eastern part of the U.S. Fall is one of my favorite seasons, so I'm excited. I am liking the new weather. The leaves change. I almost wish there was a way to put a pause on fall so I can just sit and enjoy more of the leaves and the weather. I feel like fall goes through a little bit too quickly. All right. So Esau is here. Welcome, Esau. I see Jay Gaudreau. Welcome, Jay. Hope everything is fine up in Montreal. If you recall, Ramsey is here. Raul, welcome back, guys. Welcome back to Unit 2 Office Hours. And my agenda is to crack open the NLP Mini Project. Akenduro is here. Welcome, Akenduro. I know Thursday we had a good discussion about PCA and truncated SVD. I thought that was a decent, good conversation we had. All right. So my agenda is to go through the NLP Mini Project. But as always, I always take a look at the chat, see what other things people bring up and mention that we can also talk in depth about. So as always, if there's certain other things that you want to see me talk about or explain office hours, now's the time, right? Put in the chat all throughout office hours so we can have that in mind as we go through. Okay. So do let me know. I will go ahead and start looking at this mini project. So we completed ML. Let's transfer over to the NLP Mini Project. And as the name implies, it's going to all be about natural language processing. And our task here is let's go ahead and learn how to associate good reviews on Amazon. We have a data set of product reviews on Amazon. And these reviews, these products, as you're probably familiar with Amazon or a lot of e-commerce websites, is rated from 1 to 5 stars. Low, 1 star, or as high as 5 stars. Let's create a machine learning model that learns to predict a rating given a review on the product. I see Peter is here. Welcome, Peter. So that is our task at hand. Renato is here. Welcome back, Renato. Let's go and load up the data set, save down. Let's go ahead and start download the data. Data already exists, so it tells me that, hey, no need to re-download it. It already exists. And let's go ahead and load up the data. So each line in this file is a JSON, and we have a list of decoded JSON. So we have a list of perhaps Python dictionaries. So let's go and take a look at that. I can call the type of data, which is a list, and take a look at one of those examples. It appears to be a dictionary that maps certain characteristics of my reviews and their value. So in other words, we have a dictionary here. So I have things like the review ID, whether it's some sort of field helpful or not, review text, and overall is the star rating. So imagine with this data here, I want to split this into the two different data structures. As we've seen so far, as we've seen with scikit-learn, the way we create models in scikit-learn is by calling fit on x and y. So the x and y are two different data structures. So what we will do is we'll want to make sure that we have a separate data structure with those ratings. It's contained in a key called overall. It's a little bit weird. It's a little bit weird why it's called overall, but nonetheless, if we examine this here, we observe the labels for our task are stored in the key called overall. A little weird, but that's just the way it is. So that means I can go ahead and take my data for every row, for every x in data. I'll call it row because you can think of it as representing a row in my data. I can pull out the key overall. And now, just to make sure, if I take the length of my data, 60,000 observations, and I take the length of ratings, 60,000. So a prediction for every observation in my data. I pulled out X and my Y. X is my data, Y is my rating. Any questions we'll have before we move on? All right, I see Sabine is here, and they are saying, "Hi, Don, can you please partition around something mediodds in your agenda?" A little further. "Hi, Don, can you please partition around the medioids in your agenda?" I'm not sure what you mean by medioids. I can go ahead and maybe perhaps you mean to lay out formally my agenda for today. I can go ahead and do that if that's what you mean there. So my agenda for today is simply the NLP mini project. But as always, I can talk about additional topics that you bring up that I find relevant for the time being. So NLP mini project is my agenda. All right, see Mickey here is here. Mickey Rat is back. All right, glad to see you again. Other questions people have? The cluster algorithms. We talked about, that's not the agenda. I mean, I don't have that on my agenda formally. But that is something that, if that's what people want to talk about today, or one of the things we want to talk about today, I can gladly talk about clustering algorithms. And as always, when you want something to talk about, a little more description about exactly what you're looking for will go a long way for me to prep to talk about something during office hours. All right, so I'll take that as you want to know about clustering algorithms. Anything in specific about clustering algorithms you're hoping to pick up from today's office hours? I can put that on my agenda, clustering algorithms. But anything specific about them that you'd like to know, so I can keep that in mind as I review them, as I talk about them. Do let me know. I will keep an eye out there. But nonetheless, I want to doing a little bit of the NLP mini project today. All right, I'm going to continue on. There's a note we make here that the data that comes in is a list of dictionaries. The data that the grader uses is a list of dictionaries. So we need to make sure that we keep that in mind as we go through, as we build our models. So something like pipelines will go a long way to ensure our model works both for training but also for prediction. We get a list of dictionaries, so let's make sure whatever model we build accepts a list of dictionaries. Of course, they might transform that into a dictionary or sort of data frame that makes it more useful to use, but nonetheless, it's good to know when we go into what the form of the test data would look like. So the first approach, we just simply want to do a simple bag of words model, the simple bag of words model, where if we recall in lecture, the bag of words model says, I'm going to take a document, break it down into the individual words, and count the frequencies of those words. A simple frequency count of the words in a document. A document is a unit of analysis, so here a review is my unit of analysis. A document doesn't have to be one sentence or multiple sentences, it's just our unit of analysis. What makes up a single observation, a single row in my data? So I'm going to go sketch out my workflow, what I want to do. So here comes my data. That has multiple keys, associated with it. Here comes my data. And what I want to do is I want to go ahead and pull out. I want to pull out, select the column called review text. Remember there's a column called review text? I want to pull that out. The next step I want to do is I want to vectorize those documents. Vectorize those documents. And finally, I can have my predictor. So here is my three-step process. So I got to select out that review there. Let me ask you, any suggestions on how I should go about selecting the reviews so I can then first thing I'll do is select those reviews. Any suggestions on how I should go about doing that? I have all this superfluous stuff in my data, but I just want the reviews. How should I go about processing that step there? Suggestions, recommendations. Well, I've got several approaches here, right? I can do what I did in ML. Remember in ML, I had a separate transform that pulled out those reviews, the same way you got the rating. So I can do that, or I can encapsulate that as a step. Now, I'm kind of curious to see what the form of my data is from the grader, just to verify. So I'm kind of curious. So I'm going to go ahead and say print the type. I'm going to say lambda x, and print out the type of x. My data is a list. Okay, my data is a list. So why don't I just go ahead and print out a slice of that list and see what I'm working with there. So it looks like what I have there is a dictionary. I'll look at just one observation, and it looks like I have a dictionary of just one key. In fact, why don't I just print out the keys just to verify? All right, so it looks like I have simply a list of dictionaries of just one key with just as a review text. So what I've learned here, is that the grader is going to give me a list of dictionaries with just one key. Okay, that's fine. Put that there. And previously we had this column select transformer that we built ourselves. But this is no longer 2018 or 2019 when I had to do such tools in scikit-learn. Let's see if we can do this, use a little more modern tools with scikit-learn. And that is through the column transformer. So I actually want to build this model, build my process here using the built-in column transformer in scikit-learn. So let's actually live in 2021 and not 2019 and use the built-in column transformer. What we'll do there is we'll go ahead and work with our data just to simply select the reviews. So for X and data, so we're going to put our data, before we do that, let's reformat data to be exactly the same form as the grader. So if the grader just has a single dictionary with just one of those just one key, well, I can say review text. Actually, now I'm kind of curious to see dictionary pop. I know I can pop things of a dictionary in Python. Can I give it more than one key? I might be able to give it more than one key. Let me just play around with that. It's gone. Let's see, can I pop more than one key? Maybe not. It's worth a shot. Actually ignored it. Yeah, it ignored it. Oh well. So I can go ahead and just say here, review text. And there I go. Reforward my data just to be exactly the way the data came into play. So now what I can go ahead and do is I can say form column from scikit-learn, compose, let's import our column transformer. Got my column transformer there. Call it selector. Well, let's play around with this column transformer. Let's understand how it works. So the way it works is we give it a list of steps. Those steps are tuples. The first step, the first index of that tuple refers to the name of that step. Well, we called it arbitrary, but it's perhaps useful to give it something readable. The transformer itself and the columns to apply the transformation. So in my case here, I want to come in my list of dictionaries. I perhaps want to transfer into a pandas data frame. And then the next thing I want to do is I want to select the column called review text and apply it my count vectorizer. I see that Raymond is here. Welcome, Raymond, back to office hours. So what I'll do is let's go back what we did before and let's create that custom transformer that's going to convert a data set into a pandas data frame. Right? We could have that conversion be handled in the transformers themselves, but let's do separation parameters. Have a transformer that's just solely focused on that transformation. So I called it two pandas, or two data frame, I believe. Two data frame. Class. Two frame. Accepts the base estimator, and perhaps it's best to spell correctly. So it's frame, not frame. Transform mixin. Define the fit method, and there's nothing that needs to go on fit. In fact, I would simply return self in the meantime, but let's flesh out the transform method, because one of the things we saw earlier on that maybe makes sense that we first write the transform method, and then that will infer how to build the fit method. So I'll simply have fit return self. Whether that's the final form or not, we'll simply go back to that. So self and x. What I want to do is I want to check if x is a pandas data frame. So if instance this x is of a PD data frame, let's just make sure I import pandas as PD. If that's not the case, then let's return a data frame of my x. And since when I fleshed out my transform method, there was nothing I need to learn, nothing I need to use that I learned from my data, the fit method is simply return self. So once again, I've crafted a custom transform that will convert my data into a data frame. So now my workflow, if I revise my workflow here before my selector step, is a two data frame. And then what I'm going to have to do is I'm going to have my selector step. My selector step that will apply the count vectorizer and then give it to my predictor. Okay. I see a couple people are, see Charles is here. Welcome, Charles. I see Nezrin. Hello, Nezrin. And Ramsey says, instead of return self, can you pass in fit? You will not get things to work out. You could say pass. You could say pass. However, this will cause an error. We can use pass. However, what we build will no longer be 100% compatible with the scikit-learn ecosystem. So yes, we might be able to get away with it by simply saying pass. But one of the things we want to do is we want to ensure the tools we build in scikit-learn are 100% compatible with all of everything else. We want to make sure the custom transform that we build works with grid search, works with pipelines, work with select transformer. Because if not, then certain errors might appear. And what's happening in scikit-learn, there's an assumption that the fit method returns itself. Because it's going to use some sort of method chaining that might break if I do not return self. So I can maybe get away with it at times, but whatever I build may not be 100% compatible with scikit-learn. So it's very important that we always return self in any custom estimator we build ourselves. Other questions we'll have before we move on. I created my first transformer. Now I'm going to convert it into a data frame before I move on to the next set of steps. All right, can we return self in it? I guess let's see. Let me think about that. What if we return self in init? I think we'd be fine. Honestly, I think we'd be fine, but, well, now I'm a little worried because the init method there's a new method, a dunder new dunder, that I believe is using the dunder init method as well. I would say that maybe if we do get away with it, we probably can. In fact, why not? Why not experiment, right? Right? What's the worst that can happen? Return self, and let's see what happens. A type error. Well, there it is. So I cannot. Type error. Init should never return anything. Should always return none. And since there's nothing to initialize, I could just say pass. I could say pass. Or I can simply just omit it all entirely. So it either say pass or not have it at all. The init method should never return anything. As I sort of thought of, and I was correct there. Right, that's how we experiment, right? Sometimes the best way to answer a question is to try it out. Other things we want to bring up right now. Okay, let's go ahead and move on. Rerun that cell. And now I'm going to apply from sklearn. Let's see, feature extraction, text, import my count vectorizer. Import my count vectorizer. And now I have my selector. I want to apply. I'm going to call that step, I don't know, I'll call it maybe vectorizer. I want to apply my count vectorizer. And I want to apply to the column called review text. Got my selector to work out there. And now I can build, let me build my model. So pipelines, the first step there is my to data frame. I call this converter, more generically. To data frame. Then what's next is my vectorizer. Call this selector. And I call this vectorizer, because that's what it is, vectorizer. A little more readable there. A name error because I didn't run this cell again. But I'm looking for a predictor. I get my two-step there. I can go ahead and try to experiment and start playing around with what I built. And bag of words, fit and transform on my data. Get a name error. Name instance is not defined because I have a typo, right? Name errors are oftentimes typos. It's called is instance. It's a built-in, so it should have been highlighted, so that should have been a flag to me. Oh well, we make mistakes. We bounce back them quickly. Fit and transform, it's taken a while. It's taken a while. Lots of data going on there. But let's see if this works out. That seems to have worked out. Okay, so that gives me confidence to put my predictor. And since I have a regression task, let's go ahead and have a very simple predictor. Some sklearn linear model. Let's import ridge. Let's use that as my predictor, as my regressor. So my regressor step, ridge. And since it now has a predictor, I cannot call fit and transform. I simply call fit. And of course, I forgot to give it my y. Let me close that and give it the ratings. Let's see how well that does. What's a vectorizer? So a vectorizer is a transformer that takes unstructured data and vectorizes it. So what does it mean to vectorize something? Remember what we had is we had reviews. We had a list of reviews. Hello there. This is a review. This product was not worth my money. This is a great product. So I have all these lists of reviews. Notice that there's really no structure to this data. I have rows, or you can think I have rows, but remember one of the things is that these ML algorithms, these predictors, they need numerical tabular data. They need data as rows and columns, numbers. All these here are numbers. And because data rarely comes into us a nice format of rows, columns of numbers, there's all these pre-processing steps involved to get my data into the right format. And since I'm dealing with reviews, text, where are the columns? Where's the columns in that regards? So I need to vectorize my data. You can view that every row in this here is a vector. A p-dimensional vector. Number of rows n, number of columns p. So that's what we mean by a vectorizer. It's like binarization. Define binarization for me and then I can tell you whether that's what we're referring to. I'm trying to represent my data that's unstructured. Look at this here. How is this columns? Where are the columns? And I'm creating columns, creating vectors of each observation. That's what it means to vectorize. So that ran. May not have done so good, but it ran. I have a trained model. Let's see what its training score is. Let's see how well it performs. So 0.75 r squared. Well, it could be overfitted. Who knows? And now I give it to the grader, and I do a horrible job. And just to go back to that, what happens about the vectorization, let's take a sample. Bag of words, and I want to go fit everything up to the last one, and I can say transform, and I give it to my data. And what I'm going to get back is a vector, a matrix, rows and columns. So this is what I get out. What came in was a list of reviews, and what came out was a matrix, 60,000 rows, this many columns. Our binarizer, okay, so the binarizer, let's see that. Let's understand exactly what is that doing. So I can learn binarizer. It's the pre-processing module. According to a threshold. So no, it's different. A vectorizing is different from the binarizer. Binarizer looks to binarize things, 0 or 1. Vectorizer is just a generic term that refers to how do I take this data that might be semi-structured or not structured, so it's not so obvious where the columns are, and impose a structure, represent those observations as vectors, quantities that are representing a p-dimensional space. I know it's a little bit mathematical here, but I basically have gone from these reviews, this text here, which don't have structure, right? Where are the columns? And I've created columns for each of these observations. Now these observations have columns, can be represented by a vector. That's what it means to vectorize. And there are various vectorizers in scikit-learn, including the count vectorizer, hashing vectorizer, TF-IDF vectorizer, dict vectorizer. How do I create structure in my observations? Questions people have. Is it converting the strings to ASCIIs? Well, when you say an ASCII, do you mean an ASCII, the numerical ASCII value? What do you mean by converting it to ASCIIs? ASCII encoding scheme. ASCII values. No, it's not converting to ASCII values. That could have been one encoding scheme, right? How do you convert these words into numbers? I could convert them to ASCII values. But what I'm doing is I'm applying the bag of words model, the count vectorizer. The count vectorizer applies the bag of words model, which is simply counting the number of times each word appears in the document. Yeah, right. So that's how it creates numerical values. It goes through the entire corpus, the entire body of text, and it counts for every row, for every observation, it counts the number of times each word appears. So it's a counter, so to speak. At the very base load is a counter. And every every column is a word. So there's over 6,000 words in my corpus across all documents, and every row tells me how many times each of those 6,000 words appeared in the document. And since there's going to be so many zeros, it's actually better that I store it as a sparse matrix. What do you mean by vector, right? Yes, a mathematical vector. A matrix is a set of vectors. Every row is a vector. Every row is represented by a p-dimensional space. Here, every document is now represented by a vector of 66,000, of length of 66,000. My question to you is, why did I do such a horrible job from the grader? Right? Less than 0, negative 0.4. Close to 0, but less than 0. Why am I doing such a horrible job? Any guesses? Why am I getting such a low score? What's going on there? Any suggestions? Exactly, Esau. Right? What parameters are we using to tune my model? I'm like, well, nothing really. I'm using the default values, right? Exactly, Esau. I perhaps have overfitting or underfitting. I've not tuned my hyperparameters. Exactly, Esau, right? Let's talk about tuning my hyperparameters. The sparsity is not going to affect how it learns from the data. So that's not the issue. The issue is I didn't tune my model, right? I just simply use the default values, which can be okay, as we saw in the ML mini project. Sometimes those default values are enough for us to get a decent score. We should properly tune these. So let's go ahead and do that. So from sklearn, model selection, I'm going to import grid search CV. I'm going to create my grid search object, but since it's very slow to tune, I'm going to have a very coarse grid. Since I'm going to use my ridge regressor, the most important hyperparameter for ridge is my regularization parameter alpha. I'm going to tune a log space for alpha. And since it's such a coarse grid, I'll just go ahead and do it manually here. So 0.3, 0.1, 0.3. Let me try 1, 3, and 10. Something rather coarse. Let me just try it out, see what happens. Param, I'm going to pass it my ridge, param grid, 5 folds, and verbose equals 1. Let's give my grid search right there. Let's run the hyperparameter tuning. It's going to be a little slower because I have to test them out. So 25 candidates. So sorry, 5 candidates, 25 fits. Let's see what is the best answer. Still running. Slow process. I know Pete's lots of data, right? 60,000 observations over 60,000 columns. But we should be clued in the fact that we might be overfitting. Overfitting tends to happen when I have the number of features I have sort of outweighs the number of observations. The ways the models can adapt to data is just so much more than given the examples. So I'll probably have overfitting. It's just taking a while. We'll just let it run its course. But let me know if there are anything we want to bring up right now. Yeah, and it's still running. Maybe I should have even a coarse grid. Oh well. Sunk cost fallacy. Not going to quit halfway through. Can you explain what's happening with the regressor once you have a sparse matrix? Yeah, so the sparse matrix is just a different way to represent the data in memory. Instead of having a place in memory for all the values of the array, which is the typical way you would do it, a full matrix as it's called. You just memorize the non-zero values and where they're located. So the exact format, the layout of the data we give to the regressor is different. The physical way it's arranged in memory is different. But conceptually, it's still a matrix of data. It still represents this numerical table. It still represents that. It's just physically it's laid out differently. So the regressor, some regressors can work with data arranged physically different in memory without any issue. So the regressor says, hey, I need tabular data, rows and columns. Physically in memory might be arranged somewhat differently, but since it represents tabular data, rows and columns, I'm okay with it. How it's actually using that physical difference, I don't know. It's a very deep implementation level that I'm glad that scikit-learn has abstracted that away from me. This is still running. All right, we're going to let that continue on because I do want to shift gears and let this continue and talk about clustering. Someone mentioned, hey, clustering, what about it? I'll talk about it. So clustering is a unsupervised learning technique. Unsupervised learning. And since we're dealing with unsupervised learning, we're not going to make use of labels. No use of labels. We just have the data. So in clustering, we give an algorithm a data set. Let me just draw you some data. A data that exists in a p-dimensional space, which here I'll just draw as 2 dimensions. I'll draw a set of observations here. And what I tell the algorithm is, hey, can you group the data into, let's say, 3, 4, 2 groups? I need to tell the algorithm how many groups I want, and it will look at this data and create groups based upon similar points. That's all what clustering is about. So if I tell my algorithm, can you group this into 4 sets of groups? It says, okay, well, I'll create a group here, a group there, a group there, and a group there. So at a high level, what these clustering algorithms are doing is we give it a data set. We give it the number of clusters to identify, or groups to identify, and it proceeds to separate my data into these k number of groups. And the most popular or most common clustering algorithm out there is called k-means. So that's what's happening at a high level in clustering. We give it a data set, identify me these k groups in that data, and the algorithm proceeds to identify those groups. Questions about clustering at a high level before we go in a little bit deeper? Okay, let's go a little deeper. And this is probably still running. It's still running. Oh well, we got time. So you might be wondering, so how exactly is identifying these groups? How to use clustering as a form of feature engineering? All right, so we could say, okay, well, how do we go about creating these? We could think about it as some sort of dimensionality reduction, right? Or maybe feature creation. If we take a look at this here, I can perhaps create a column, create a feature that tells me which group this value exists in. Or you can think of this idea of clustering as creating identity. Saying, okay, you even view generically as creating labels. Right? Or creating some sort of value for each data observation. What I could do is I can run the clustering algorithm. So I've identified these groups. These are the properties of these groups. If you give me new data, or even this data here, I can go ahead and create a new column that tells me which group it belongs to. Group 1, 2, 3, and 4. And now I can view that as an additional feature. So I could do that, right? I can use this identified groups as a new feature in my data set. And since these new features are categorical, we can perhaps treat them as, like, let's say, one hot encoded. So that's how I can use clustering as a form of feature engineering. And some of these unsupervised learning algorithms are typically used in conjunction with supervised learning. Just like you use dimensionality reduction in the sense of with supervised learning overall. As Maurice pointed out, how can you use this for feature engineering? Engineer new features that tell me which cluster it's in. This is still running. Other things people want to bring up right now before we go a little bit deeper what's going on in these algorithms. Okay, so what's going on deeper in these algorithms is this k-means algorithm. What it's doing, it's starting off with an initial seed points of what it thinks should be the center of the clusters. And then it applies an iterative algorithm that goes about shifting the center of these points to identify those clusters. The way it does so is, okay, these are my initial starting points. Let me assign all my data to a cluster, and let me shift that star point depending on the resulting center of my cluster. That shift potentially might change members of the resulting clusters, so it reapplies the algorithm again. Until it has converged. Now, since we're doing distances, since we're calculating distances, we should use scaling. You should scale your data. Well, that's what's going on with k-means, perhaps the most common clustering algorithm. What is bootstrapping? Bootstrapping is a term that is used quite often in various fields. So because it's used quite often in various fields, it's going to mean different things. So in the sense of, so generically bootstrapping is from a phrase in English that says you've got to pull yourself in the bootstraps. It's sort of a way to get up, you get yourself up, I guess, is to you pull your bootstraps. And I don't exactly ever tried that before, but it's a way to kind of pick yourself up. So bootstrapping is basically a way you can kind of pick yourself up. Start from you've fallen down, you've got to get yourself up. You only have so many things. You've got your boot braces, your boot laces to pick you up. I guess that's where it comes from. But unfortunately, this term is ubiquitous across various fields. It means different things depending on the context. So in the context of machine learning, you often hear the phrase bootstrapping to refer to this idea of sampling with replacement. In an ideal world, you have an infinite large training set. In an ideal world, you have an infinite number of training data sets. However, you don't have that in real life. You don't have an infinite amount of data. You don't have an infinite number of training sets. What you could do is you can try to pull yourself from the bootstraps and try to make the best of what you have, which is a single data set. So here is a single data set. And what you can do is you can sample from this data set here and create a second data set. You can sample from points here, replicate them, and put them into the second data set, the second bag. So bootstrapping refers to taking your single training set, sampling with replacement, sampling from that training data, always with replacement, so that ultimately you come up with a new data set. Yes, it's derived from the old one, but it's different. And maybe we can use this different data set to help us out. For example, train decision trees in a random forest. In cross-validation, you can do bootstrapping in cross-validation, but the cross-validation refers to how do I go about cross-validating my model. I can do k-fold cross-validation where each fold is a separate data set. But I can also use bootstrapping, right? What prevents, nothing's holding me back from using bootstrapping to apply a cross-validation strategy. And this is still running. Hopefully it at least finishes before the end of the hour. So anytime you hear bootstrapping, oftentimes in machine learning, it means this idea of creating new data sets from just a single data set. And it's used for, specifically in random forests, a different data set for every tree. Now going back to clustering, k-means is just one clustering algorithm. And it's going to fail when you try to identify clusters that are no clusters in data that aren't necessarily rounded or round or spherical. So let's say I have this data here. Okay. If I tell, by observing this, by just looking at this here, and you ask me, give me 3 clusters. For you to give me this data set, if you were to give this to a human would say, you know what, looks like there's one cluster here. And since you want 3 clusters, there's probably a cluster here and a cluster there. We ourselves can come up with these elongated clusters. But k-means is going to fail to identify these elongated clusters. The reason being is because the way the algorithm works, it's based upon distances. Distances, how far are you away from each other? So a point here and a point there, while we say they should belong in the same cluster, are pretty far apart. So a k-means algorithm may not identify these elongated clusters. So we believe our data should be put in these elongated clusters, something like k-means will fail to identify those elongated shapes. It might pick up things like this there, and there. So if we believe we have elongated shapes in our data, k-means is going to fail. So instead you should rely on a different clustering algorithm called Gaussian mixture models, which basically says in my data, in my space, I have a mixture of k number of Gaussians. The thing about Gaussians is that I can play around with the mean and the standard deviation, the mean, its position of the cluster, the standard deviation, the spread of the cluster, and the covariance matrix, which expresses how much elongation I have in my cluster. A more complicated algorithm for sure was able to handle these complicated shapes. I see Ramsey has a question here. How long does it time have to pass before I think we've done something wrong? Well, the fact that I set verbose equals to 1 is telling me is going to print out what's going on. So I actually know that something is running. However, it's still taking a long time. So to answer your question is you don't know, right? You don't know. right? We do things like set verbose equals to 1, so we know what's going on. I probably should have set verbose equals to 2, which is actually even show me more things. So we want some sort of, confirmation that something is running. I'm getting some sort of confirmation. And it's just lots of data, not much memory. It's going to be a slow process. That's just the way it is. All right, additional questions we'll have. Anything about clustering? Can you do batch machine learning? What do you refer by batch machine learning? Let me know what you mean by that. I mean, in some sense, we're doing some sort of batch, right? We create models, and we see, we create them, and we see what happens. Could you separate the results to be? Could you separate results to be combined? What results are you referring to, and what do you mean by combined? I know, I'm sorry if I'm being a bit dense here, but what do you mean by separate results? Right? I could, if I have a data set, I could, this large data set to make predictions on, I could create it into groups, right? If that's what you're referring to, take my data set and break it up into chunks and say, predict on this chunk, predict on that chunk, predict on that chunk, and glue it back on together. Well, you can. However, it may not be. So two things, right? Two things going on here. Can you train it in a batch? Yes, you can. Can you predict in a batch? Yes, you can. Predicting on a batch of data. So in other words, you have 1 million of observations you want to make a prediction on. Should I break it up into 1 million? No, not 1 million. Can I break it up into smaller batches? And you can, especially if one batch you can't hold in memory, and then glue back all the results. Nothing, because each prediction is independent. So there's nothing preventing you from breaking that data into different batches and making predictions on those separate batches and gluing them back. Nothing, because predictions are independent of each other. Now, training's tricky here, because in some regards, giving me the entire context of my training data might be useful. So some algorithms can be trained in batches. Not all algorithms, but some algorithms can be trained in batches. And now that's probably what you're kind of hinting at here, is the fact that if it's going really slow, why don't I just try to train in a batch of the data? So maybe apply something like online learning. So maybe we'll have to try that out on Tuesday and see how long that takes. Online learning, this idea of sequentially improving my model as I give it more and more batches of my data. Yeah, so that's a good segue into Tuesday. Anything else we want to bring up right now before we conclude? I guess I'll have to tell you how long it took and what the answer was. Because it's using the entire training data to come up with the beta coefficients. How to use PCA components to determine importance? Well, the beauty of PCA is that PCA will already tell you the order of those components already in the order of the most important. So the 0 index, the 0 column, most important component. 1 index, the second most important, and so forth. So the beauty of PCA is if I tell you, hey PCA, give me the 5 new features, give me the 5 best new features, it will only give me the best. And they can be ordered in such a way from 0 being the most important, 1 being the second most important, and so forth. So scikit-learn already handles that for me. All right, anything else we want to throw in there before we conclude? And it's still running. All right, we'll have to conclude. I'll let you post on how long this took and what the result was. Take care, everyone, and see you on Tuesday.